Hi, welcome to CHEM2005, the chalk and talk summary. Today we will talk about the pyridine. Okay, what is a pyridine? Basically, a pyridine is a 6-member ring with a nitrogen, it's a heteroaromatic, and as I told you, it's aromatic. Why? Because we have 2, 4, 6 electrons, cyclic, all the variations are sp2, sp2. That means will be planar, therefore this will be aromatic. It's following the Hooker rules. An important thing about it is that this pair of electrons of the nitrogen, okay, this pair of electrons, don't confuse with a negative charge. I will draw it a little bit better. This pair of electrons of the nitrogen are in a sp2 orbital, are not part of the aromatic, are not part of the aromatic because the pz orbital is used doing this double bond. That means are available, and pyridine will be a base. Okay, that means that one of the most typical reactions is we have the pyridine here. And we have the pyridine. Okay. Basically, pyridine is a good base. Okay, we will talk about the order of triethylamine, this type of bases. Okay, basicity. Okay. Another important thing about the pyridine is that, as I told you, we have 6 electrons in 6 atoms. But one of the atoms is a nitrogen that, as you well know, nitrogen is by far more electronegative than not carbon. That means this nitrogen will attract more the electron, more the electron density to him. That means that if we do the math, what we will have is that each carbon has less than 1 electron. Okay, because if 6 electrons in this atom is 1 for each, but we know that the nitrogen will take more than 1 for him, the rest will have less than 1. This indicates that the pyridine is electron poor. Just the opposite than our friends, the pyrols. What means is electron poor? Electron poor means that is working badly in electrophilic aromatic substitution. That means that will not be a good substrate. That means, remember that with pyrrole, for example, we have this. Okay, remember, we use this and we get the nitration. Yes? In benzene, we need to add nitric acid and sulfuric acid, and we get the nitration, that means stronger conditions. With pyridine, what we will need is a stronger condition. I mean, we will need nitric acid, sulfuric acid, and heating, and we will get okay. That means it's very difficult to do electrophilic aromatic substitution in the pyridine. If we are able to do it, that is very difficult, what will be the orientation? Well, pyridine if we want to do electrophilic aromatic substitution, will go to the meta position. Okay, always because it's electron poor range, this nitrogen orientates meta. Okay, meta to the nitrogen. If we have more than one substituent, then we have to do the sum of all the orientation. But basically, the electrophilic aromatic substitution happens very rare, very few times in the pyridine. Okay? Again, when we are doing, and this is important, when we are doing activation, remember that we have to go through the carbons and never through the nitrogen. Okay, like the same rules that we explained by pyridine. However, if the pyridine is electron poor, that means it's going bad, it's not working well with the electrophilic aromatic substitution, will be a very good substrate for nucleophilic aromatic substitution. Okay, will be a very good substrate. Okay, remember the nucleophilic aromatic substitution. For example, this is a pyridine. Okay, and we have here a leaving group. Remember that the leaving groups normally are fluoro, chloro. Okay, bromide is by far worse leaving group for the reasons that we explained it in the nucleophilic substitution of the aromatic. We are following the same rules, and we add a methoxide. What we will get is the substitution of the methoxide for the leaving group, for the fluorine or chloride, to obtain the final product. Check that if we want to do the same with benzenes, what we need is an activating group, a nitro electron bourgeois group in ortho-para. Here, the only that we need to do is to have a pyridine. The pyridine is enough active to do this reaction very fast. Okay, the active position for the nucleophilic aromatic substitution are para and ortho. Okay, if we have a leaving group in these positions, the reaction will take place without any problem. Okay, in meta will not work, or will work by far worse, more slow. The rate will be very slow. Okay, right? Okay, then this is the nucleophilic aromatic substitution. But you know that we like to twist the reactivity of the things. That means what we want in organic chemistry is that the pyridine is able to do electrophilic aromatic substitutions. How we can do it? How we can do it in order that pyridine will go well in electrophilic aromatic substitution well. What we need is to transform the pyridine in a pyridine N oxide. How? With an oxidant MCPBA. Okay, you can use also H2O2, but I recommend MCPBA, it's easier. What we get is the pyridine N oxide, that basically is this. Okay, it's this compound with a charge, negative charge on the oxygen and positive charge in the nitrogen. And now this ring, this aromatic ring, becomes electron rich. Okay, this aromatic ring becomes electron rich and can do any reaction that we do with the benzene. I will do the integration again. And the orientation will be ortho-para. That means normally will be para because ortho has more aesthetic effects. That means if we add a nucleophile here, electrophile here, will crash with the oxygen. That means that the easier position is okay. It's not only activated by the electrophilic aromatic substitution, that his orientation is orthopara regarding the nitrogen. And then the only that we need is to remove the oxide. We use PCl3 and we get the final pyridine that we do the activation in the para position, we get the substitution in the para position. Right? This is how we do electrophilic aromatic substitution with pyridines in an easy way. Okay, remember, for example, what I can do is remember that if we do exactly the same reaction with the pyridine, first of all, will not work well. We will need to force the conditions. Second, the orientation will be meta instead of para. Okay, this is the most important reactivity of pyridines. Poor substrate for electrophilic aromatic substitution, very good substrate for nucleophilic aromatic substitution. If we want to do an electrophilic aromatic substitution, our option is to oxidize the pyridine to pyridine N oxide, and when we have the pyridine N oxide, basically is an active ring for the electrophilic aromatic substitution. We do any reaction that we can do with benzene, okay, and the orientation, remember, is changing to orthopara, while the orientation in a normal pyridine for the electrophilic aromatic substitution will be meta. Okay? This is all that what I want to explain about the pyridine. This is the most important, how to change his reactivity, and see you in the next lesson.